Hey, Thomas. Thomas from the
Hey.
airport with sunglasses on. Look at
Yeah.
that. Hey.
Hey.
Oh, hey, Ramses. Look at that. Oh my God, he's growing up so fast. This is amazing.
Yeah, he's huge. Yeah.
He's huge, man. I saw him like a year ago.
Yeah.
Oh my God, that's
He's
crazy.
aging. Yeah.
Okay. I'll let you guys travel. Just make me host very
Yeah, I
quickly.
just did. I think you should have complete control.
Wait. Yep.
And
Perfect.
this looks great.
Awesome. Nice, Thomas. Okay. I will let you be. Enjoy your flight, yeah, and I'll see you in Lisbon.
Yeah. I'll see you in the weekend or something, right? Or when are you arriving?
Friday.
Okay. Yeah. I'll let's be sure to have coffee or something.
It'll happen. Ciao, ciao.
Yeah. Ciao. See ya. Good luck, eh?
Thanks. Hey, can you hear me as well? I'm a bit stressed out because this is the first time
Yes,
ever.
I
Okay,
can hear you.
wonderful.
Yeah.
All right, cool. Do you have an idea how many people do we actually expect to have, or?
Mostly I think around 30 or 40 or something.
Awesome. Okay, that's good. And you can see my screen properly, right? It's like
Yes, I
the
can
whole
see
thing
everything
shows.
perfectly.
Okay, awesome. Okay, more people are showing up. Thanks. I don't know. By the way, at what point? I'm not quite sure what Thomas has already done. I think you guys have already done a bunch of fMRI lectures, right? It's just the
Yeah.
sort of MRI physics side of things that. Okay.
Yeah, I was already wondering also why this lecture is more near the end of the course, because it seemed logical to have it more in the beginning, but
Yeah, I know what you mean. I think also when I was doing my master, we typically would do it at the beginning, and I
Yeah.
think I had a discussion with Thomas about this. Just he thought that can be a bit more of a physics heavy side of things, even though the lecture is not really, but he thought people may find it a bit scary or something. I don't
Okay,
know.
yeah.
Maybe it depends, I think.
I don't know. Oh, by the way, you're already recording, but I'm not sure if
Yeah.
you. Okay, yeah.
I think Thomas started it already. He was.
Oh, he already went in and then went away.
Yeah, because I'm not the host, right? I was not, so he had to log in. He started recording as well to make it easier for me. So that's a bit awkward, I think, because I'm not. Anyway, I don't know.
Oh, you can. I think you can cut it out if you want to, but you don't have to.
Probably, I don't know.
But
Yeah, I don't know.
yeah,
I think that was the idea, basically.
yeah, makes sense.
I don't know. Did you guys already do the tutorial, this sort of case-based stuff that we?
Yeah, I think it's he uploaded it, I think yesterday.
Okay.
So I'm not sure if everyone already took a look at it, but
Yeah, there is some overlap, but also not that much,
okay.
I think. So I don't know. But yeah, I guess at the end you can always ask me questions. I don't know how you would normally do this, right? But like, I don't know, it would be nice if you just interrupt me at times, because it's also
Yeah.
very weird if you just talk to your screen, basically.
I can
Right.
imagine. Yeah.
With no social interaction at all. It's just bizarre. But anyway.
Yeah, I think you can say to everyone that everyone
Yeah,
can interrupt.
yeah.
I think probably there are gonna be questions about the heavy physics stuff. So
Well, there's not a lot of heavy physics, to be honest, but
okay.
anyway, it just. So you're AI students and psychology students, right?
Yeah, it's a combo. Yeah.
All right. Nice.
Yeah. So I'm doing the neuropsychology master. So I thought it
Oh,
was
wow.
quite an intense course, to be honest.
All the fMRI statistics and stuff.
Yes.
Yeah, I know what you mean. I think it's yeah, it can be a lot, I guess. But to be fair, I'm sure the AI people feel the same, right, about the neuroscience. So
Yeah, exactly. I think there are some gaps for all of us. So yeah,
yeah,
makes sense.
I don't. Yeah, I don't know. It's I don't know. I still feel like I have no idea about the neuroscience side of things, to be honest. So I'm just vaguely worried every time I open my mouth and say something about the brain. But that's what happens, I guess. That's normal.
Yeah, of course.
Anyway,
So what is your background?
yeah, I did well, basically what happened, I did my bachelor in engineering, and then I found that to be pretty boring, and then I sort of switched to neuroscience, or tried to. But it turns out I'm still not good at this whole neuroscience thingy. I'm more of I don't know, I guess I'm more comfortable with the MRI physics side of things. But anyway, somehow I gravitated in this sort of vague MRI thing. Now I'm the Spinoza Center, as you can see at the
Yeah.
bottom.
Yeah,
Where
nice.
we basically do ultra high field stuff. You guys are all in the VU, right? The
Is that-
Freie. You
what?
guys are all in the Freie Universität, right?
Yeah, exactly. Yeah.
How's that happening, by the way? Are the lectures live now, or?
It's a combo. Yeah, it's hybrid, so you can choose
Okay.
either to attend at the VU or from home.
Mhm.
But I think there are a lot of people who don't live in Amsterdam, so they prefer to
Yeah, I get that.
stay at home.
I
Like
guess
I.
it's cheaper, right?
Yeah.
Not having to pay the Amsterdam rent, but yeah.
Yeah. So did you also study at the VU or did you study somewhere else?
No, so well, I did my bachelor in Athens,
Mm-hmm.
and then I somewhat randomly ended up in Nijmegen. I think basically I applied for the Amsterdam one, I think for the one that you are doing now, but they wouldn't have me. So, so I ended up in Nijmegen. That's the truth. But then I ended up doing a PhD, which was partially in Maastricht and partially elsewhere in the US. And yeah, now I'm here, I guess. So
Nice.
yeah, it's fun.
Very cool.
Oh wow, it's a lot of work to admit all the people in suddenly.
Yeah, I'll shut up and then you can do your your things.
Yeah. I mean, talking to people definitely helps make me less nervous, but it would be nice if we can get more people in in a conversation as well. Okay. So typically this is like an hour and a half of a lecture, right? So 45 minutes a break and then 45 minutes more or so, right? I guess.
Yeah, I think so.
Okay.
Yeah. Or I think you even have until yeah, I think you have until 3:15.
Okay. Well, we should be done before that, I hope, but let's see how it goes. There are not that many slides, like 30, so should be possible. Are you guys all looking for internships as well? After your master or?
Yeah, we just started our internships a month ago, I think. So it depends on if you do a research or a clinical track. So the people with
Oh
the
yeah, of
clinical
course.
track
Yeah. That
do a
makes
different
sense.
kind of internship.
Yeah. All right, 25 people, that's not bad at all. I guess people are still coming, so let's give them a few more minutes. All right, guys, it's 3 minutes past 1:30. It seems to be slowing down the people joining, so maybe, okay, I was wrong. More people are joining, but maybe we can get going anyway. Oh, wait, Demi's already asking if the guest lectures are exam material. So I'm not 100% sure. I think you should ask Thomas, to be honest. I think so, from what he told me. I think we also have a tutorial which should cover part of what we're gonna discuss today and sort of expand on a little bit on it. But yeah, maybe check with Thomas as well to be sure. Can you guys all hear me clearly? Now's your chance to let me know if it's not very clear. Okay, awesome. Yes, Demi, please do. So it's also a bit, I'm supposed to be talking for like an hour and a half or so, right? I mean, obviously with a break in between. Basically, it would be nice if you just interrupt me from time to time, either, just say something or just ask questions in the chat or whatever you feel like. I mean, I don't have that many slides, it's like 30 slides. The idea is to sort of cover the MRI physics basics. So it's more of it'll be nice if we can do it more of a discussion than a sort of one-way thing. It's not very heavy on the actual physics side, so no equations or anything, more of a sort of understanding the concepts kind of thing. That is the target. Does that make sense to everyone? All right, I guess I'm gonna get going then. Cool. You can all see my screen, right?
Yes.
Awesome. All right. So hi, everyone. I'm Nikos. I'm working, oh, wait. Chat still. Yeah. I'm Nikos. I'm working at the Spinoza Center for Neuroimaging. I'm a colleague of Thomas there. And he asked me to talk to you a bit about, well, the basics of MRI and how we can apply this to neuroscience. I tried to come up with a funny title, but that didn't work very well, but still, anyway. We already were having a discussion with Fairley about why we're doing this sort of more basics lecture towards the end and at the beginning. And the reason for this was that, well, we had a chat with Thomas at the beginning, and basically you don't necessarily need to understand the physics to sort of analyze the data, for example, fMRI data, but it can give you a bit of nice background and a bit of an insight on how you can improve your data further. So I thought it was a bit more of an advanced topic, maybe, and that's why we do it now towards the end. But basically, the idea is to talk almost only about MRI today, which I think is basically this amazing technique in a lot of ways. I mean, compared to PET or EEG or other stuff, basically you can examine so many different contrasts that do so many different things. So it's really quite cool, and it's very unique in that you can also look inside someone's brain basically without almost any safety issues, without doing anything to them. It's pretty magical in a lot of ways. So I'm gonna carry on. First of all, the idea was to sort of talk a bit about how we actually produce the MRI signal. How does that happen exactly? I don't know if you have guys discussed this at all already. I got the impression that you have not, right? Okay, so anyway, the idea is basically quite simple with MRI. We have two different components to it. First of all is what we call the nuclear magnetic resonance phenomenon. Second of all is what we call the K-space. And I'm going to go through both of them, but it's literally, MRI is literally just the combination of these two different things. And the first thing, the nuclear magnetic resonance part, is literally just what you do to produce signal. You literally just use it to record some signal out of the nuclei. And the second part is basically to encode where this signal is coming from in the brain. So if you have, say, the front part of the brain or the back part of the brain, and you want to sort of differentiate where the signal is coming from, we use what we call K-space encoding. And that's literally all that MRI is. And you'll see that a lot of the challenges that we sort of face with all of these brain imaging techniques are quite similar in a lot of ways. So for example, also with PET, for example, if you think about it, there is this, I don't know if you have talked about it at all, but there is this limit in the resolution that you can reach, because exactly it's quite hard to figure out where the signal exactly is coming from. And MRI is very unique in that it has it's very powerful in terms of being able to encode where the signal is coming from exactly. And I will explain to you a bit later on how this works. This works exactly, and it's kind of similar as well to all of these analysis techniques that you have already done, I think, for fMRI. It's really very powerful in this regard, and in my mind, it's one of the best features of MRI overall. So first, the nuclear magnetic resonance phenomenon on its own. I mean, we basically have 3 words there. Sorry, I'm interrupting myself all the time to add people in, which needs to be done by the host. Okay, so we have 3 words there.
So do we already have access to the PDF? Because I can't find it on file.
I don't think you do, actually, no.
Okay.
So you will probably have access to the recording, I think, and I will send you the PDF, but I think I cannot do it myself. I need to ask Thomas to do it because I don't have access to all these files, but yeah. I don't know, I think in a week or so you should be able to have it. Is that okay?
Yeah, sure. We could also download it if you send it in the chat, but okay.
Yeah, exactly. Okay, awesome. Cool. So we have 3 words there, right? We have, okay, more questions in the chat. Oh yeah, that actually may be a good idea. Can someone else take the sort of adding people in duties? That would be great.
Yeah, if you make me host, one of the things you can also do is go to participants.
Yeah,
and
not
then you
someone
can,
else, right? Okay.
And then disable.
So who wants to volunteer for this duty?
I have been a Zoom host last year, so if you give it
Okay,
to me.
but I don't know who you are.
Oh, Bibian.
Okay.
Borst.
Oh yeah, wonderful. Okay. No.
But I think it might challenge it with, okay, yeah, I'll make you.
Okay, I made you co-host, Bibian.
Yeah.
I think if you can add people, that would be great.
Yeah.
You can also interrupt me if there are questions in the chat that I'm not seeing, for example, or something like that.
I just disabled the waiting room. That's the easiest way to do it.
Awesome, thanks. I'm not an expert with Zoom stuff. All right, so as we said, let's start again from this. We have 2 different things, nuclear magnetic resonance and K-space, right? A nuclear magnetic resonance is a phenomenon, basically a physical phenomenon with which we produce a signal, basically. And K-space is how we encode our spatial location, right? Okay, so to create signal, we basically have this nuclear magnetic resonance part, and you can already tell from the nuclear part that has something to do with the particles, and the magnetic part basically means that we need a very strong magnetic field to produce this. So I don't know if you have seen an MRI before ever. It basically looks like that, right? It's this giant tube with a bed, and in this direction, you have a very, very strong magnetic field. This is the North Pole, this is the South Pole. People have mixed them up during the installation, at least that's the sort of legend, and then you destroy the scanner if you do the North Pole in this direction. But the idea is that you have this very strong magnetic field. Essentially, you create this by having this very, very tightly wounded coil, essentially here, these windings. These are kilometers and kilometers of a coil, and we keep this in a sort of superconducting condition. So essentially we put them into a temperature that's very close to absolute 0 and with liquid helium, and we run a current through it, and that creates a very strong and homogeneous magnetic field through the middle, right? And that's what we call the B0 magnetic field. That is a basic characteristic of MRI. So you probably have heard of people talking about a 3 Tesla MRI or 7 Tesla MRI or 1.5. This is basically what they're talking about how strong this magnetic field is, right? This is an extremely strong field, by the way. This is something like 60,000 times the Earth's field in a normal 3T. And if you go to higher fields, it gets obviously even stronger. The reason we may want to go to higher fields is basically that we get more signal, more SNR, and we can make better images out of it. That's about it. Does that make sense so far? Awesome. Okay, so for nuclear magnetic resonance to produce our signal, we need this very strong B0 field. And why is that? Essentially, let's take the sort of basic MRI application. Essentially, we have a bunch of water protons in our head, right? So we have a lot of water protons that sort of spin, precess in a random orientation. And what happens if we turn on a very strong magnetic field is that they start aligning themselves along with this B0 field. Essentially, they act like tiny little magnets in practice. So they align themselves either parallel or anti-parallel to your B0 field. But if you sum them up, they sort of have more of them are in this direction, basically. So that creates basically this sort of nuclear magnetic momentum in your brain. And what happens if you apply then a second small magnetic field, a brief radio wave, is that they sort of orient all of them in a different direction, perpendicular to the main magnetic field. What you basically give them what we call spin coherence, essentially. And this creates then a very small current that we can pick up. So that's the signal, essentially, that we are measuring in practice. So the idea is we have an extra second coil that from which we emit a little second radio wave, and then we synchronize all our water protons in one direction, basically, and then we create a small current that we can pick up. That's literally it. So this is frequency dependent. So essentially the frequency that we will apply here, that's exactly what we're gonna measure out. Does that more or less make sense? It's, I mean, you're gonna sort of have to trust me on this. It's just how this physical phenomenon works. It's literally just that you have a very strong magnetic field, and then within this, if you give them a second radio wave, basically the water protons in your head will resonate with this in this frequency, and we can measure a radio wave out of them, basically.
Can I add
Yes.
something for like my own picture? Because now you kind of give them that like their RF signal, and then it's gone, and it's gonna try to move back to the previous position then, right?
That's absolutely correct, and I'll get into that in a bit. So this is a sort of permanent field, and this is a very brief one, and then this one go back to the initial condition, and I will explain a bit how this goes and how this helps us in creating contrast in a bit, but you're absolutely right. Yeah. Yeah. All right, so this is basically the main idea of how we create signal in MRI. This is just a physical phenomenon that we discovered. I think roughly the very first applications of it were discovered like 100 years ago, more or less. And it started being a bit, it was put more in formal setting, I think, by Bloch and Purcell in the 1950s or so. They got a Nobel Prize for this. And actually, we don't have to do this only with water protons. NMR is used throughout chemistry in all sorts of ways, and people also in MRI use it to look into other things than water protons. It's just that we have so much water in our bodies that basically water protons what we most commonly use. It's a very helpful and useful thing to do, basically. That's about it. So if we want to sum it, basically, the NMR part of things, how we produce our signals, basically a combination of this very strong magnetic field, B0, and a second radio wave that we emit with a second coil, and then we measure some signal. So we have a transmit coil to emit the radio wave and a receive coil to measure the signal, right? Okay, and with this, basically we have a basic phenomenon and we can already measure something. So this was developed, as I said, by Bloch and Purcell, and it's based on what we call the Zeeman effect. And I sort of added this because it has a funny Amsterdam side history there. I don't know if you have ever walked into the Plantage Muidergracht, it's next to UvA, but basically there's the Zeeman laboratorium, and a lot of the experiments that sort of set the basis for MRI were done there. And I don't know if you walk down the street, it's quite a nice street, you can sort of stop in front of it. Okay, there's something in this in the chat. Why is the resonance important? And doesn't matter which particular B1 we emit. Yeah, so that's a very good point, actually. So the resonance is basically important because that is what we can measure, right? So essentially, we sort of apply a radio wave to the water protons, and then this emits some signal. But the thing is that, as we'll go into it in a little bit, different parts of the brain, based on the properties, basically emit signal in a different way, different strength, and that's the way that we create contrast. And does it matter what particular B1 we emit? Yeah. So essentially, depending on the nuclei that you want to apply to target a different B1 in practice. And the resonance is crucial indeed. So I'll talk a little bit later on about how the MZ, your magnetization vector, exactly behaves in practice. And you'll sort of maybe get a bit of an inkling on why we can sort of measure it in a particular orientation versus others. Okay, so I hope that covers your questions, Philip, more or less. But you can let me know if you want to discuss this more. Okay, anyway, so we have the NMR signal, right? But we basically still have no idea where the signal is coming from. So at this point, basically, if you have signal from the position A in the brain and the position B, it basically completely overlaps. We haven't added any sort of way to encode the signal location. And we sort of figured out a way to do this. And that goes back a bit to what you were asking also, Philip, about the frequency of the B1 signal. So essentially, the idea is that the frequency of the signal that you get depends on your B0 value itself. So how strong your main magnetic field is. So what we do, the sort of genius part of MRI, is that we add a little bit of a change in our B0 value depending on where we are in the brain. So for example, if we're a little bit on the higher side of the brain, then we don't have, say, 3 Tesla, we have 3.1 Tesla. And if we're a little bit more at the bottom, we have 2.9 Tesla, for example. This actually too large a difference. It's a lot smaller than that, but just to give you a bit of a description. And what that happens is that the signal from the bottom part of the brain resonates at a slightly different frequency than the top part of the brain. So that means that if I have, say, some signal from this side and some signal from this side, I can sort of differentiate them based on the different frequencies that I record. Does that make sense to everyone? Okay, so obviously this encodes my signal only in this direction. And obviously MRI is basically a 3-dimensional signal. So we have similar ways to encode the signal in all 3 directions, but I'm not gonna go into how this works exactly because it gets more complicated. But this is the main idea, that we sort of we slightly change our value of our B0 depending on where we are in the brain, and or in anything that we sort of want to image, and that helps us encode the signal location. Okay. And this basically what we call, essentially we encode the location as frequency, and this is what we call the K-space. And I think in your tutorial, you'll sort of see what a K-space looks like. This is the raw data that we get straight out of the scanner, more or less. And it definitely doesn't look like a brain image at all. But still, essentially, if we want to sum up what MRI is, it's the NMR part at different frequencies, depending on where you are in the brain, and they all combine together. And it's created with this B0 field, this added B1 transmit and receive, and also some gradients that slightly change our B0 value so that we know where we are. And this is literally all the basics of MRI that you need to know. That's how we create and how we encode our signal. Yeah, is this clear so far? Are there any questions maybe? All right. So you may have, oh, wait, there's something in the chat. Awesome. Okay. So in the tutorial, you may have seen some images. I think actually Thomas posted online just yesterday, so probably you didn't. But anyway, if you go there, you will see some images. Oh yeah, so Philip had also a question in the previous speaks. Yeah, so I'm not sure if you refer to this part of the call, so the B one or this. Essentially, this is literally just what we call a birdcage call, basically that it just emits a radio wave and then it records. It's also, it can record the radio wave. In practice, these are two separate things. It can also be the same thing, depends a bit on what you want to do. In modern systems now, they're separate. On this side, oh yeah, the right one. On this side, basically, it's we just use these gradients to run very small currents, essentially, to kind of adapt our B0 field a tiny bit, basically, just to help us with encoding the precise location. But I don't think you really need to go into more detail than that. And it also gets very hairy and very confusing for me as well. So maybe we'll just skip that, going into more detail into this. But yeah, anyway, so you guys have probably not seen the tutorial yet, but essentially you'll see we have some images that look like that. And this is basically the signal that we get straight from the scanner. So if you just grab some raw data before they are reconstructed, it looks like that. So very bright in the middle and a lot more noisy on the side. And essentially what we record here is a bunch of frequencies, literally. So we have slower frequencies in the middle and higher frequencies in the end. And what we actually want to get out of this is something that looks like that, right? The brain image in practice. So how does this work exactly? I think you guys have done some time series analysis and resting state stuff. So you've probably seen a way to get from frequency to time series and time series to frequency, I would guess, right? This sort of Fourier transform kind of thing. So it's a similar concept here as well. We literally can use a Fourier transform to go from the sort of frequency space to the actual brain image space, right? So I will repeat it, the sort of what MRI does is we basically record, essentially we encode space as frequencies. So it's a sort of real life Fourier transform. And then by applying a reverse Fourier transform again, we can go back to our initial brain image. Is this clear? Okay, we have a question. Oopsie. Okay, that's awesome. All right. So we literally record a bunch of frequencies and then we go with a Fourier transform, we reconstruct our brain image. That's literally all we do. What I would like to point out, and I think we discussed this as well in the tutorial as well, that this is not a one-to-one reconstruction. So it's not that this point in the Fourier in your K space corresponds to this point and this point, for example, to this point, right? But instead, the whole of K space helps to reconstruct every point in the brain image. That's just how we combine the frequency. That's just how Fourier transform basically works, right? So we don't go from one point to one point. That's sort of important conceptually. So if you look at your K space in practice, in the middle you save the sort of slower frequencies, and on the side the higher frequencies. Yeah. So basically, if you want to get a higher resolution image, the only thing you need to do is to basically record a larger K space with higher and higher frequencies, and then you can push it towards higher resolution. So you will also know that it's a lot brighter in the middle than towards the end, and this is because we sort of, one of the properties of K space is that a lot of the SNR is right in the middle. And this is basically in terms of how the sort of signal tends to adapt. So to sort of demonstrate this, we also have this in the tutorial, but if you try to reconstruct only the very central part of the K space, you can already get a very recognizable image. This is obviously the Mona Lisa. It looks a little bit blurry, as you can see, and this is because we have emitted all the higher resolution frequencies on the side of the K-space. And if we instead try to reconstruct a signal with a simple Fourier transform just from the sides of the K-space, then we just get the edges information, right? Does that make sense? I think you will apply this in practice in the tutorial and you'll see how this goes. But this is important to sort of understand how some of the MRI artifacts play out. And what I mean by that is, for example, you can imagine that there is some sort of artifact in when you're reading out your data. And for example, you have a very bright spike in this spot right here. The way this can translate in your actual image when you reconstruct it is a sort of stripy thing along your whole image, right? So it's not very obvious why, how some artifacts basically translate. You have to look at the Fourier transform properties themselves to sort of figure out how MRI artifacts get created. You have to sort of think of the mathematical properties of it. But anyway, so if you want to push further the resolution, you can just make your K-space larger and larger and encode more and more higher special frequencies. Of course, that comes at the cost of extra noise that you add into your data, but that can still be okay up to some degree. Anyway, so another point that is kind of interesting is that you can see here that you have this sort of 2D space, X and Y, and one of the properties that sort of follow is that the MRI signal that we save is a complex number itself. It has a sort of magnitude value and has a phase value as well. So it's literally a vector. I guess you have all worked a bit with vectors before, right? Sort of real and complex value. In practice, most of us just play with the sort of magnitude MRI image. So we mostly tend to ignore the sort of phase value of our signal, but it's still there and it's still useful to have. And it's important that you know that the sort of MRI signal that we're recording is complex conceptually in terms of interpreting a bit some artifacts, as you'll see, I think, in your tutorial. Yeah? But in practice, for example, for your fMRI signal, you'll get a bunch of these magnitude images that we can just interpret. Oh yeah, do you get these two images separately? So in practice, what you get is literally this sort of complex K-space right here, that if you just apply Fourier transform to this, you'll see that you get a magnitude image and a phase image. So they just happen at the same time. And typically with an MRI, you can sort of specify whether you also want to save the phase image or not. Typically, you don't need to, and the phase image tends to be a little bit less robust, but you do get them by definition at the same time. Yeah, so I literally mean mathematically complex. I mean that you get a complex number. So it's basically something that's A plus IB. That's literally what you get for every point of the brain. Yeah?
Sorry, what's the magnitude and the phase again?
So that's literally in every voxel, what you, so if we go back a little bit, right? Say that this is the MRI image that you get, right? Straight from the scanner. It literally looks like that. It's a bunch of frequencies. So if you apply a Fourier transform to it to sort of figure out what your brain image looks like, in practice, you will get a combination of magnitude and phase. So it's literally like, it's just a property of the Fourier transform that if you transform from, if you put something in the Fourier transform, you'll get a complex number out of it in practice. Yeah? So it has a magnitude part and a phase part. It's just a complex number. Every voxel basically that you get is, it has a complex number. In practice, we just sort of get rid of the phase because it's not extremely insightful in most cases. And we focus on the magnitude. Did this answer your question?
Yeah, I was just wondering what does it mean that you get a magnitude and a phase? What is magnitude? What is phase?
I see what you mean. Well, have you played a bit with complex numbers maybe before? Like you can think of it as a bit like this, that if you sort of have this sort of XY sort of array coordinates, right? but it has some value in X and some value in Y, so that you also have an added, that somewhere in the complex space, let's say, instead of in a single line.
Okay.
Does that make sense?
It's okay.
Okay.
Thank you.
Right. Okay. So essentially, we want to go back, and I know I'm repeating myself a lot, but still it's important. If we think of MRI, we basically have the B0 and the B1 fields to create our NMR. They have some encoded gradients. We encode where the signal is coming from based on frequencies. And then we apply again a Fourier transform to recreate our brain image. Yeah. And that's literally the basis of MRI. That's what we do. So the only thing that's still left there is to sort of think about how we can produce tissue contrast, and then we're done. That's literally it. And I think you guys already asked me some of it, so I suspect you already have a bit of an idea about how this works. But let's go with this. Okay, so the idea again, by the way, do you want a break, or this is also a good time to sort of ask if there are any more questions? Okay, then okay. So essentially, Demi, I would be up for a break. I think now have been like, what, 30, 35 minutes in. So the contrast sort of side of things takes 10 more minutes. And then I sort of carry on a bit with examining some applications, the safety part. So it's up to you guys. I don't know what you would prefer. Would you like to do okay, so let's do a 10-minute break now, and then I don't know, meet again in 2:15. Is that okay? All right, cool. See you guys in a bit then. You can also ask me questions in the meantime if you want.
There is one question in the chat.
Mm-hmm. Oh, whoopsie. Sorry. No, you're right. Okay, I hope that answers your question about the encoding gradients. Well, okay, so that's a good question about the Fourier transform. Essentially, what we do in practice is the MRI machine, it's literally the NMR part and the sort of real life Fourier transform part, and that's implemented by the encoding gradients. So literally, the encoding gradients take advantage of the NMR phenomenon that depending on your B0 field, you'll get a slightly different frequency back, right? And we essentially use this to literally make to make a real life Fourier transform. So basically, we use this little encoding gradients to adjust at what frequency our signal comes from. So in practice, this acts as sort of encoding your spatial location in a sort of through a sort of real life Fourier transform somewhere. And then we can reverse this by applying again a Fourier transform. And in practice, you'll see that the inverse of the Fourier transform and the actual Fourier transform end up having the same result. It's essentially the same mathematical operation. But yeah, that's about it. And they're the calls which give the relative. Yes, you're absolutely right. They are the calls which give a relative change to the constant b0. That's it. And they also do a bit of what we call the sort of extra encoding mechanism. So that's the phase encoding, which I think I talk a bit about it briefly in the tutorial, but that's basically it. Yeah, you have it exactly right. That they encode the relative change to the constant b0. Oh, but that's nice. I'm sort of glad that you understand this part, because I was a bit worried that it was too high level and abstract.
So can I ask something?
Sure, yeah.
So we use different frequencies to understand where the location, where we are in the space.
Mm-hmm.
And then we also use different frequencies to understand the tissue, right? Like different tissues give different frequencies, right? Or activation, the activation is different.
That's not quite, no, I don't think so. The short answer is no. Well, it depends a little bit. I'm not quite sure what you're referring to, Asin, but you can, so for example, you can examine water protons and other, for example, if you want to do something like GABA spectroscopy or whatever, then these also sort of tend to resonate at different frequencies. So maybe that's what you're referring to. But in practice, in terms of sort of standard MRI, we sort of assume that we just care about the water protons themselves. So we care about, for example, the water protons in white matter and the water protons in gray matter, or the water protons in CSF. And that's all that we focus on, basically. And all of them, because they're water protons, they all basically they have the same chemical structure, and they all resonate at the same frequency.
Okay, so that's for the anatomical, right?
Also for fMRI. So also for fMRI, it's literally the same thing. We just sort of measure a little bit the change in deoxyhemoglobin, right? But we still measure water protons.
Okay, and we measure water protons, and we measure the change in deoxyhemoglobin.
So there were some interruptions, I think. I don't know if it was from your side or my side, but can you repeat the question, because I missed it?
Yes, we measure both. So in fMRI, we measure both the water protons and the changes in the hemoglobin.
Right, but so essentially, it's still a measure of water protons. It just has to do with how the blood flow and the blood volume and the oxygen consumption rate sort of affects the signal that we end up measuring. We're still measuring water protons, just that we measure the water protons in your blood, basically.
Mm-hmm.
Does that make sense?
Yes, yes.
Okay.
I'm just trying to understand. Yeah, maybe you would discuss about later. How do we distinguish between the tissues? Because I thought that we distinguish
so that's
based on frequencies.
Well, no, not quite. I mean, you can in some ways, but that's not how basic MRI works. Basically, the sort of standard implementation of MRI. Essentially, the way we produce contrast between different tissues. Well, I will explain in a bit, but essentially the idea is that the sort of magnetization vector that we have behaves in a different way depending on when you apply the B1 in practice, and also the size of it as well is different, and that tends to produce some contrast that we can use to image, to create some contrast basically in our image. That's
Okay.
yeah. And someone was asking about the relative change. Yeah, so that's an important concept as well. So, okay, I'm not going to start sharing my screen yet, but the idea is that, for example, you can essentially with NMR, the frequency that you get, it's a property of your B1, but also your B0, and also of the sort of whatever thing you're targeting. So, but if you're targeting, say, water protons, if you apply the same B1, then the signal that you'll get, the frequency of the signal that you'll get will depend heavily on the value of your B0. So if you adapt a tiny bit your B0 value, so if you go, say, from 3 Tesla to 2.9 Tesla, and you apply the same B1, the frequency of your signal will be slightly different. So essentially, what we get by that is that when we measure our signal, we get two different signals that overlap with each other. We get a slower frequency one and a faster frequency one. And with that, we sort of encode the spatial location of where the signal is coming from, because say from the bottom of the brain, you'll have a bit of a slower magnetic field, a bit of a lower magnetic field, so you'll get a bit of a slower frequency signal. This is a very small difference, but it's enough for us to sort of figure out where our signal is coming from exactly. Does that make sense, Kuhn? Awesome. Yeah, then I think that's quite important actually to understand. As in basically this also explains why. Yeah, exactly. This allows us to locate where the signal comes from in the brain, and also creates all sorts of artifacts. As in basically we really have to be extremely accurate with our B0 values, and any sort of artifact there will completely make us miss where the signal is coming from. So a lot of artifacts of MRI come from that, basically. And actually, I think this initially, when we were still doing NMR, we hadn't really discovered MRI, this was just showing up as distortion. So you'd get a sort of drop in your B0 value somewhere in the bottom of your sample when people were just doing spectroscopy with that. And this would appear sort of signal with a different frequency, and then they would try to get rid of it. And they were trying to make their B0 field more homogeneous and things like that, basically. And then someone had this genius idea that they could use these B0 changes, basically make them on purpose to sort of encode the signal location. And then we had MRI. And people also got Nobel Prize for that. It's really quite ingenious. All right, so 2:15. I think we're supposed to sort of carry on again. All right, and you guys can see my screen again, right? And everyone is back. All right, so let's go back a tiny bit. We basically discussed how we produce signal, right? We had the NMR phenomenon, and we had this sort of encoding gradients to kind of encode our location, and we combine this to figure out where a signal comes from, where in the brain. But we still right now we don't have a way to produce tissue contrast. Okay, there's something in the chat from Philip. Measuring signal result. Well, so that's just the property of the NMR phenomenon, Philip. Sorry, maybe I should have read this question aloud. Basically, he's asking why the water protons resonate at different frequencies. Is that right, Philip? Okay, maybe he doesn't have a microphone. Okay, so this is just a property, basically, maybe I should explain this a bit better. This is just a property of the NMR phenomenon, that essentially the frequency of the signal that you get depends linearly on your B0 strength. That's literally it. So if you vary by tiny bit your B0 strength, you'll get a slightly different frequency at which they resonate. So there is this thing, I think you guys can Google it. It's called the gyromagnetic ratio. This is a property of, for example, the water protons and everything else you may want to image. And that is a set value. But to sort of figure out at what frequency your water protons will resonate, you can just multiply this with the B0 field, and that's the frequency that you get. So for example, if you want to, and that's basically literally what we do to create signal from different spots of the brain. You can multiply your gyromagnetic ratio with 2.9 Tesla or 3.1 Tesla, and you'll get a slightly different frequency signal. Yeah, does that make sense? All right. Okay, so this is how we create signal. And now what we want is to create some contrast. So we can, for example, differentiate between white matter, gray matter, blood, CSF, all of these things, right? So if we go again to how our protons were when we had this B0 field, as I told you, I think we sort of, if we sum up how all these little magnets behave, essentially we have a little magnetization vector in one dimension, right? That's literally what we have. And this right here at the bottom is what we call the transverse magnetization. So it's the magnetization in this direction. This is basically what we measure. At this point, when we don't do anything else, then we don't apply a Bion field, it's basically completely zero, right? So right now, basically we're recording no signal. So if we have someone in the scanner just lying there, the B0 field is on, but we don't measure a signal. But when we apply a Bion field, we sort of tip our magnetization in some to sort of be on the transverse plane. And here, at this point, we can measure some signal. We can record something out of this. Also, we can measure basically a small electrical current, right? The problem is that this magnetization, it doesn't stay there, but after a few milliseconds or seconds, depending basically on what we measure, it goes back to its initial condition, back to this. Yeah. And then at this point, again, we have no signal. But the thing is that how fast this happens, that heavily depends on the tissue that we're trying to measure. So essentially, white matter, for example, may go back faster to its initial condition compared to gray matter. And the reason for this is that, for example, if you think of white matter, you have all these actions, etc. So all of these sort of spins tend to bump against each other and kind of lose their coherence more quickly than, for example, gray matter or CSF. Okay, so I'm trying to check the chat at the same time and can get a little bit confusing. So the sort of confusing part of this is that essentially we can measure either this or this part in some ways. So essentially we can also tip this in this direction to mention it, but basically how quickly the longitudinal magnetization recovers is also a separate property of how quickly the transfer relaxation goes back, but we can measure both in different ways. So what I mean by that is that, for example, if you look at the sort of longitudinal magnetization, so what's happening in this dimension, essentially when we start from this point, when we just have our B0 field, when we apply an RF, it goes almost to zero. For example, if we apply a 90%, a 90 degrees pulse, and then it slowly grows back together, and we have a curve through which the signal grows back, right? So we go from this to this. And this is what we call the T1 rate, right? So you may have seen some anatomical images, for example, an MP rate or a T1 weighted image. That's literally, basically, they sort of measure at some point how quickly the T1 rate grows back, right? And you can also measure how quickly the T2 or the T2 star or the transverse relaxation rate goes from horizontal to, goes from zero to, okay, how quickly basically this goes back to zero, basically. So when we apply an RF field, we sort of have a strong signal on the transverse plane, and then it sort of decays quickly to 0. Yeah, does that make sense? Okay, so we can either measure this part or we can measure this part in practice. And there's this difference between T2 and T2 star rate. I'm not gonna talk a lot about this, but in practice, basically T2 star is what we actually observe in practice. So it's the observed decay. And essentially it's the T2 rate with some sort of added inhomogeneities that are systemic. And the T2 part is basically the sort of random loss of coherence. I'm not going to go into this because I think it's just going to get confusing. But the important thing to remember is that the T1 and T2 and T2 star rates, all these decay rates, are characteristics of the tissue. So depending on where we're measuring, so depending whether you have gray matter or white matter or CSF, the rates are different. And in that way, we produce contrast. So for example, if you have, say, the T2 star rate of water or gray matter or white matter, you'll see that they decay quicker. They decay in different ways, and that way we produce contrast. So for example, if we measure the transverse magnetization after some milliseconds, after we apply an RF pulse, we'll get a different value of T2 star. And from that, we sort of get a different signal intensity, and we can image our water and our gray matter, white matter, and get some contrast. I hope that made some sense. Doesn't this influence the processes? From Oleg. Sorry, Oleg, I don't really understand the question. Can you either expand or maybe if you can also speak up? Yeah.
Yes, I'm sorry. Can you hear me well?
Yeah, I can hear you, yeah.
Great. The question is, if we, for example, try to put some particles inside our head under the magnetic field, doesn't this actually make the processes inside our head different than they were without any intervention?
You're absolutely right. That's true. I was sort of examining here the very sort of simple case, let's say, of what we already have in our head. But you're right that, for example, there are all of these experiments. I don't know, you may have seen it, for example, these Mayon experiments or stuff like that, where essentially you can add a contrast agent into your body. So, for example, you can add something that's a little bit, for example, rich in iron, right? And they say goes through your brain, right? Admittedly, we don't do this in humans. I think sometimes people did it in animal research. But essentially, if you have more iron nanoparticles in certain parts of your brain, this shorten your T2 star value a lot. So the T2 star value is very sensitive to iron concentration, and this definitely interferes with what you actually measure. In a way, if you think about it, the bolt contrast, so the fMRI contrast that we measure, it's essentially the same thing. It's basically also a contrast agent in a way. So it's essentially what we get with the dextrohemoglobin is that we have a sort of a little bit of richer, we have something that's a little bit richer in iron. So in a way, it acts as a contrast agent in practice, and that changes our T2 star value. It makes our T2 star a little bit shorter. Does that make sense, Oleg?
Yes, but it is still distinguishable, right?
Oh yeah, we can still, so essentially you can think of it like this. We can measure the signal from every single voxel, right? So if you think of this single voxel that we have, you can assign it a T1 and T2 and T2 star value, right? And that heavily depends on, for example, how much water you have in this voxel, how much myelin structure you have in this voxel, how much iron you have in this voxel at any given moment, right? So this will essentially decide how quick your T1 and T2 and T2 star decay rates are, basically.
Okay, thank you.
Yeah. Yeah, so Kuhn was also still asking about the difference between T1, T2, and T2 star. It's not a stupid question at all. It's really quite confusing. I'm going to go back a bit. So it basically goes back to this, right? So you can think of the sort of sum of your magnetization at rest, it looks like this, right? And then if we apply an RF pulse, essentially we sort of tip this magnetization somewhere else. So and this sort of grows back to its initial condition. So for example, we are here, and then we apply an RF pulse, and for example, we tip the magnetization to the transverse plane, and then it will grow back to this one. And essentially, how quickly this grows back determines our decay rates. So the T1 rate is basically how quickly we go from this back to this. And the T2 star rate is basically how quickly we go from this to this again. Does that make sense? Ken? Okay, so the difference between T2 star and T2 is basically the T2 star is what we observe. So if we do a simple experiment and we go from this to this, that's basically our T2 star. T2 is a sort of extra property. Essentially, it's the T2 star value, but only its random loss of coherence. And the T2 star value is basically the T2 with some added signal loss that happens due to inhomogeneities. So in practice, for example, with BOLT, what we typically measure is the T2 star value. The T2 is still important in terms of predicting how our signal will behave, and also as an extra contrast mechanism. That's about it.
And they are like completely different scans in a way, right? Like you can.
You're absolutely correct. Yeah, I'll go into this in a bit. You're absolutely correct. Yes, exactly, Vivian. And then Philip had a question.
Sorry, before you continue about this T1 and T2, can you explain one more time what T1 is?
Yes. So we are in this sort of initial condition, right, of our magnetization. Our net magnetization is in this dimension, in this direction, along with P0, right? And then we apply an RF pulse, and for example, we tip our magnetization in the transverse plane, right? So essentially, our T1 rate is how quickly we go from this part to this part here. So how quickly this grows back to this. Yeah, so how quickly we recover our longitudinal signal. That's the T1 relaxation rate.
Okay, so if I look at the image, then if you would talk about T1, is it the difference between the green arrows?
Yeah.
And the T2 is the different, is like the tip between the like the aqua.
Exactly. You're absolutely right.
Okay, great, thanks.
Yeah. Okay, and Philip had a question. The K-space signal depends to the B0 gradient and signal amplitude. You're absolutely correct, Philip. Yeah, that's exactly it. Essentially, the signal amplitude and the rate it changes depends on the decay rates of the different tissue types. That's exactly it. So this is literally all that MRI is. We have the NMR part, we have the sort of signal encoding part, and the decay rates basically control our contrast. And with that way, we have a way to produce a signal, a way to sort of determine where the signal is coming from, and we also produce some contrast. Cool. All right.
I have another small question.
Yes, please go ahead, Vivian.
Like when you go back to the previous slide, because you're gonna try to turn all, like pretty much all the hydrogens into the plane you want, but I assume that they don't all move back at exactly the same.
Yeah, rate. You're absolutely correct. So if you think of all of these, so essentially all of these water protons act like tiny magnets, right? And what we saw here is a sort of simplification. So we saw the sum of all of them, essentially. So it's you're right that some of them are already have relaxed. It's a random process, basically. Some have already relaxed, and some are all over the place. But if we add them all together, they point there, basically. That's it.
And then and then when they kind of said like the relaxation time is like when a certain amount of them have went back.
Yeah, it's literally a half-life measure. Yeah.
Oh,
yeah. All right, cool. So as we said, this is a characteristic of the tissue. So basically, just to give you a bit of an insight, if you think of, for example, of your transfer coherence, right? So what we measure basically here, right? If, for example, I apply a quick RF pulse and then I measure the transfer plane, what's happening. For example, my water, it doesn't have any myelin there, right? It doesn't have any iron. It's basically just water protons just not bumping into anything. They will relax slower than, for example, what's happening in the gray matter and what's happening in the white matter. And the white matter, for example, will lose its spin coherence much more quicker because you have more myelin there, for example, right? So they tend to sort of transfer their energy elsewhere. And that means that the transverse magnetization will be much shorter, say, in 50 milliseconds after the RF pulse than the gray matter run or the water run. And this will mean that our signal amplitude will be smaller in white matter, right? Okay, so this is basically how this works. And essentially, whether we measure this or this heavily depends on what sort of RF we apply. So we can combine different sequences of RF to measure different things. So you'll have heard of doing, for example, anatomical scans or like T1 weighted scans. And then we basically put together a bunch of pulses to measure this, or we can put a bunch of pulses together to measure this, right? And if we want to do bold fMRI, we typically want to measure T2 or T2 star contrast, more typically T2 star contrast, basically, because it's an iron-based thing, and that's what we do. So there are two main sequences in MRI. In total, we have hundreds of them, literally, but they're all based on either what we call spin echo or what we call gradient echo. So I'm not even kidding that this is literally the basis of everything in MRI. So we use Philips scanners these days a lot in Amsterdam, at least. And if you kind of go through the whole library of how this is programmed, I mean, they have thousands and thousands of files, but basically the sequence files is literally just two files, one for spin echo and one for gradient echo. So it's literally just the basis of everything. And sort of property of spin echo is that it's the first thing that was discovered. So we have, for example, a 90-degree pulse immediately followed by a 180-degree pulse. And this is what we call the flip angle. So it's basically literally how much we flip our magnetization. So whether we flip it by 90 degrees or whether we flip it by 180 degrees, in summary, right? But I'm not going to go into detail on how this works exactly. The main thing to know is that we apply a set of RF pulses, and we have to wait a little bit until our signal basically gets big enough, so our resonance is big enough for us to get maximal signal. And the characteristic of this sort of spin echo approach is that it has a fairly high SNR. It's also how we measure T2. It's not very sensitive to T2 star approaches. And we have to wait a little bit to measure a signal. So essentially, we have to apply one pulse first, and we have to wait a bit. We have to apply a second pulse, and then we can measure a signal. And this is basically what we typically do, for example, with diffusion MRI, which you guys have probably heard about, right? If you want to do all this fancy tractography, you have some variant of this, basically. What we commonly use for fMRI stuff is this sort of gradient echo approach, where we basically just apply a small RF pulse, and then we measure some signal afterwards. And here, in my example, I just have a 90-degree pulse, but in real life, we use something a lot smaller. It's just with 90 degrees, you basically get maximum signal. But anyway, but the advantage here is that because we have a single pulse, that we can read a lot of our data, basically, and not have to wait a lot between applying our pulse and reading our data. So it's a much quicker technique. So gradient echo approaches are by definition a lot quicker. We spend more time reading data. And that's also a plus if we want to do fMRI stuff, right? Because we want to read our data as quick as possible to kind of follow the metabolic changes in the brain. Yeah, does that make sense? Okay. Oh, wait, there are some questions. Yeah, so the differences between spin echo and gradient echo, I don't think, honestly, they're very important. I think the main thing is that with spin echo, you need a different set of RF pulses compared to the gradient echo. With gradient echo, you can have a single excitatory B1 pulse, and with spin echo, you need two, and you need to wait a little bit. And they're also differently weighted. So for example, the spin echo, you have more of a T2 weight, and with the gradient echo, you have more of a T2 star weight, but I'm not going to explain why, because I don't think we have enough time. The important point is that gradient echo is quicker, it's T2 star weighted, and therefore it fits better what we want for fMRI stuff. So the sort of typical fMRI sequence is a gradient echo sequence. And essentially, because we want to measure signal very quickly, what we do is we don't just apply one excitation and then read our data, right? So when MRI just started, that's literally what they were doing. They were just applying one excitation, they were reading one line of data. Apply an excitation again, then read a tiny bit of data. In what we want to do is what we call echoplanar imaging, where essentially, if you think of your whole of your K-space, right? You say you have this K-space slice, right? Basically, we try to read this whole slice after a single excitation. So in practice, we try to spend more time reading data than exciting. And that's what we use for both the fMRI, echoplanar imaging or EPI. Okay, more questions? Okay. So echoplanar imaging is this sort of workhorse for bold fMRI and all sorts of applications for MRI. It initially was developed for cardiac imaging. You can imagine that, for example, if you're trying to resolve the cardiac beat, you need to be extremely quick. And this actually is still quite successful in that regard, but it's almost exclusively used as well for bold fMRI at this point. The problem is, of course, that if you move through the K-space that quickly, we introduced a lot of artifacts. And as I told you, these distortions heavily depend on this Fourier encoding, right? So essentially what happens is that after we excite, then we measure our data, but in the meantime, our spins sort of build a bit of extra phase information, which means that we sort of don't know anymore quite where they come from, and we have a bit of distortion. So, for example, our data may get to look a little bit like this. So the signal is supposed to be coming from there, but it's actually encoded there when we reconstruct it. So one of the big challenges for fMRI, especially if you go to higher fields where this problem is more obvious, is to try to undistort your data or to try to figure out ways to account for this analysis-wise. And you'll see in the tutorial, I talk about this a fair bit. Yeah, so basically the point to remember here is that we measure bold fMRI typically with echoplanar imaging, EPI, to be very quick, but this creates all sorts of artifacts that are mediated through this Fourier transform from K-space to actual space. I hope that makes sense. Well, you can always ask me if it doesn't. All right. Oh, and that's actually the MRI basic summary that I had already. That's cool. So if we go back through it again, signal produced with the NMR phenomenon, our signal localization is produced through the K-space encoding, right? So that's how we know where the signal comes from through a Fourier transform. We can create some contrast through the longitudinal and transverse relaxation rates, the T1, T2, and T2 star rates, and we can weigh our signal to measure either one of these basically by combining RF pulses in different ways. And the main sequence is the spin echo and the gradient echo. And that's about it, basically. That was the physics part of it that we had today. Are there any questions about this?
Yeah, I had one question regarding signal contrast. Is that I'm always a bit confused with what it exactly means. Is that we can see something on a scan or?
Okay, so you're right. So literally what we measure is a current, right? So it literally means how big our current is. That's literally the sort of what signal contrast means in this case. Of course, this is mediated through this Fourier transform, right? So the frequency of the signal what we measure is different every time, but essentially what we get after the sort of this Fourier transform is literally a stronger or smaller amplitude of our signal. That's what we get with different, that's what I mean by different contrast.
Okay, thanks.
Yeah. Any more question, guys?
Yeah, what does RF mean again in the last bullet point?
Oh yeah, sorry, I should probably explain this. Radio frequency poles, so that's our B1, basically. We tend to use them interchangeably, and I forgot to explain this. Sorry.
No worries.
Yeah, so that's our combination of B1 pulses, basically.
Okay, thank you.
Okay, cool. All right. So this is
one
the
more question.
Yeah.
Sorry. I didn't really understand where the name spin echo and gradient echo comes from.
Yeah,
Like
this is-
what spins and what is gradient?
No, you're right. You're right. I did not explain this at all. Essentially, when we sort of came up with MRI NMR experiments, people first, for some reason, found a more complex thing that they named spin echo. And it's this sort of set of pulses that you first apply a 90-degree pulse and then a 180-degree pulse. Well, there is a reason for this. Basically, what you do is you apply a pulse, right? And then you kind of refocus your pulse. So you reverse any sort of loss of coherence that you have. And then essentially they call this spin echo as in that you kind of have a bunch of spins and they resonate and they echoing out whatever you applied here, basically the frequency of what you applied. And that's what they call it, spin echo. It's just a convention, basically. The guy that invented it, I think, died. He was Erwin Hahn, and he also got a Nobel, I think. And there's an institute after him in Germany, in Essen, named after him. And yeah, I think he died like 3 years ago or something. But that's basically literally what he did. And gradient echo is this much simpler case where basically you apply a single RF pulse and you measure some signal afterwards. And that's not what they discovered initially, because this was, while this is much simpler, they basically didn't quite have the well, good enough tools to basically measure this, because it's a very quickly decaying signal. So you really need to measure within some milliseconds, basically. And they just named it gradient echo. To be honest, I don't know why they called it gradient echo, but yeah. But the main idea there, I think, is that with different sequences, with different combinations of radio frequency pulses, different combinations of B1, we can create different signal. And that for fMRI, we mostly use what we call gradient echo. I think that's the main point to remember. Yeah.
Okay, thanks.
All right. All right. So after the sort of basics of MRI, I sort of wanted to talk a bit towards the end a bit about our current applications and what we do research-wise. But I first thought it would be good to maybe talk a bit about MRI safety, and because I figure that's important. You guys probably will come in contact with MRI at some point. So the main thing to remember is that it's super safe, right? So that's one of the main advantages of MRI in my book. That if you think, for example, of X-rays or PET, they all use some sort of ionizing radiation. Here, we don't do anything like that, right? We basically just, in the default sort of MRI state, we just put someone in a strong magnetic field and we apply a simple radio wave, which is very simple, similar to what we do, for example, in our microwave. And it doesn't ionize, it's not non-ionizing radiation. So we don't know of any harm in relation to MRI. I myself get scanned like 2 or 3 times per week to test one thing or another. So it's really super safe. But the B0 field, it's always on. So there's always a gigantic magnet there that's extremely strong. So if you see accidents around MRI, it's typically something to do with the B0. So for example, someone opened the door and then someone with an oxygen tank came in and there was someone in there lying in the scanner. And for example, they ended up getting the oxygen tank right in the head, or someone had a wheelchair and the wheelchair ended up getting sucked by the scanner. So this tends to happen once or twice per year, basically around the world, and someone is injured or someone dies. So it's super important that you don't put anything ferromagnetic in the scanner, right? So you never ever do this. MRI is always on. Just be very, very careful, basically. If you ever step into an MRI room, just don't bring anything ferromagnetic. So people will always check this. There's a question about this. Black Mirror episode. I haven't seen this, no. That's a nice one. I had seen, I think, this House episode at some point where someone was bringing in metallic objects like scissors and stuff like that in the MRI room, and it was pretty uncomfortable. But anyway, okay. So that is the main thing. That's the main safety concern with MRI. There's another safety concern, not quite common, but essentially, as I told you, the sort of radio frequency that we apply, the Bion field, is essentially a pretty similar frequency to what we do in a microwave. So it can heat up tissue a little bit. In a microwave, of course, you try to heat up tissue. In MRI, we try not to. And normally we can control this. So there is a limit, basically. We sort of have all these models to simulate how a body will heat up in an MRI machine. And we sort of try to follow something like, if you keep someone in MRI for an hour, you're allowed to heat them up by 1 degree, basically. So you may go up to 37 or 38 degrees, basically, after an MRI session. But this is very well controlled, basically, is my point, that we are quite careful. You don't get a lot of heating just because of the RF. This happens essentially because when you apply a small magnetic field, like an RF field, this sort of runs tiny currents through your body, and your body acts as a resistor and heats up a bit. We can, though, this can be dangerous, though, for example, if you have a metal implant, even if it's not ferromagnetic, so even if it's not, it doesn't get sucked up by the scanner, if you have a metal implant, it has a different conductivity. So you can play an RF field, and then this can concentrate current through it and can heat up around it, basically. The tissue around, for example, an implant can heat up a fair bit. So we're always very careful with what sort of implants are allowed in the scanner. This has to be vetted very, very carefully. So if you're ever asked to participate in an MRI experiment, people will go through a list and they will ask you, for example, did you, for example, I don't know, had a knee replacement at some point, or did you get, for example, a tattoo? For example, tattoos can have a metal nanoparticle. So typically, we kind of check where you got them in the world and how recent they are, because there have been rules about this kind of thing as well, or dental implants as well. Anyway, so this is the second main danger of MRI. First, to sort of get a ferromagnetic object inside the MRI room, and second, some sort of metal implant. So that's how you also avoid cooking the brain. If you sort of have some sort of mental implant installed, then it can actually heat up your brain a fair bit, a very localized spot, very dangerous. So we try not to do this. And beyond that, honestly, MRI is really quite safe. It can be quite loud because sort of switching the gradients to encode the position has to happen very fast. So this creates these Lorentz forces that tend to basically have this very high frequency noise. So we ask you to put earplugs. Also, it's a small tube because we try to keep our B0 field homogeneous. So you can have a bit of feeling of claustrophobia. I myself, to be honest, I'm not claustrophobic at all, I thought. And then I did my first MRI experiment and I was like, oh yeah, this is pretty uncomfortable actually. So don't be surprised if that happens. And beyond that, when we switch the gradients very quickly, the tiny electrical currents that run through your body maybe will cause you a little bit of a nerve stimulation. That's not typically annoying, but you may notice it. So now you know why. And you also may feel a little bit dizzy when going through the scanner. So essentially, you can think about this as a sort of the scanner when you move through it, through the B0 field, basically acts as a gigantic TMS. So you guys probably know TMS stimulation, right? This sort of magnetic stimulation, it's the same concept basically. So this maybe it will make you a little bit dizzy for like 20 seconds, but this also goes away. Okay, there is a question here. If heating influences neural activity, well, Oleg, I don't know that, to be honest. I hope not. I don't think so. I think the people are more concerned with hitting in terms of the relaxation rates, because the relaxation rates are also affected by how hot your sample is. But I think with humans in practice, this is not an issue. So we don't keep humans for that long in the scanner to really affect the T1 and T2 values. But for example, when you do ex vivo scans and you keep something, for example, a brain in the scanner for like 20 hours, then hitting is an issue actually in terms of the relaxation rates. But yeah, all right. So these are the main safety points for MRI. Ferromagnetism is an issue, and beyond that, some heating, and the rest is basically pretty minor, honestly. So overall, very safe technique. All right. So we're nearing the end. I just want to talk a little bit about what we actually do now. What's the current state of the field, in case you guys ever drop by the Spinoza Center. Basically, what I do is a lot of work in ultra high field MRI. So this is MRI that is basically at 7 Tesla or beyond. There are not that many scanners that are above 7 Tesla at this point, but there are some. So the main reason that we go for higher B0 values is that basically we get more signal. So we get a bigger magnetization vector, and you can do all kinds of things. Specifically for MRI, you also get more contrast for various reasons that I'm not going to go into, and that is great. At the same time, we also buy into a bunch of issues. So there are a lot of technical issues in terms of how homogeneous your B0 field is, and how homogeneous your B1 field is, your RF. So, you know, we basically have to struggle a fair bit, but still we can get much more higher resolution images. So for example, I'm interested a fair bit in the cerebellum, and we can get images that look a bit like this at 200 microns. So that's basically 1/5 of a millimeter. And we can make out, for example, the foliation of the whole cerebellum, which is very, well, it's really hard to do, to be honest. Wait, I can show you another video maybe. Also, this is the sort of cerebellar cortex right here. And you can sort of inflate it a little bit, similar to what we do in the cerebral cortex, to kind of try to project, for example, fMRI results on it. It's still not perfect. There's still some segmentation artifacts, but this is the sort of thing that you can do at higher magnetic fields. You guys may also have seen this sort of line scan fMRI application from Thomas. The idea is to push fMRI to really high in-plane resolutions and really short volume acquisition times. So we can do something like 1/5 millimeter analysis and 1/5 of a second repetition time, and really measure neuronal activation in extremely accurate manner, especially and temporally. You've probably also seen all these popular receptive field applications from Thomas already. This is also fairly exciting and benefits a lot of 7 Tesla. And lastly, I would like to point out we're always looking for internships for interns. So if you're interested in MRI stuff or neuroscience, do contact us. We have this webpage. We'll have some projects, and or you can just email me as well. That's also possible. That's all I had, and I wanted to have some time in the end, maybe for people that have already looked, for example, through the tutorial and had some questions already, or maybe you guys have still some questions anyway. I'm gonna stop sharing, and yeah, that's about it. Oh yeah, someone's asking for the email. I'll just post it in the Zoom chat. You can also contact me if you have any questions about this lecture for that matter. I'll try to answer. Mind you, I'm going to Lisbon for a week tomorrow, so I'll probably not answer very quickly, but yeah. Someone's asking about the TR. Yeah, the TR is the repetition time. So that's basically how quickly we measure. That's it. Okay, do you guys have any more questions? Something that was not clear, something you would like to focus on, something you'd like to discuss from this lecture or other lectures?
I have a conceptual question, let's say.
Yeah, let's say.
I don't understand how, if we're measuring current, we end up with complex numbers. But I've also haven't worked with complex numbers in school, so I don't know if this is easily explainable, or you can point me towards some other information.
Yeah, you're right. No, you're quite right. I get why this would be confusing. Essentially, this has to do with the frequency phase of your signal in practice. That's the sort of short answer. That's how this works. Does that make sense? So essentially, your current can still have some phase, right? If you think of it as a sinusoid, basically we can sort of measure that, and that's how we end up with complex numbers, basically.
So complex in the sense that it has the amplitude and the phase information in one thing.
Exactly. That's exactly what I mean.
Okay, I got it. Thank you so much.
Oh yeah. Well, someone is asking about the sampling direction. That's a good point. So the tutorial didn't quite overlap with what I talked, because here I was hoping to be a little bit more basic, basically. Right. So top-bottom sampling. So essentially, that's a good point, Rutger. So if we think a little bit, okay, so can you sort of visualize your K-space, right? This sort of square, right? Basically, we have to kind of run through it in measuring it. For example, if you think of this ecoplanar imaging scheme, EPI, what we do for BOLD, we sort of want to measure data in all points as quickly as possible. And typically what we do is we have this sort of Cartesian grid. So we sort of go a bit like this. We kind of zigzag through K-space in practice, right? So when I was talking about distortions before, what I mean is that we sort of start measuring from here, right? And we kind of zigzag through K-space, but in the meantime, while we're measuring our data, essentially what happens is that we build a little bit of added phase in our signal, because this takes some milliseconds to go through the K-space, and that leads to some distortions in terms of where the signal is coming from exactly. So if we measure from the bottom of the K-space towards the top, or we start measuring from the top of the K-space towards the bottom, we'll get the exactly reversed distortions, basically. Does that make sense, Rutger? Okay, so this happens a lot. I mean, it sounds like a very stupid technical issue, but it's not something that's trivial to solve, especially with 70 or higher fields, because this gets more pronounced, basically. It's easier to build up phase in your signal, so things become harder. But we can solve it exactly by, for example, measuring our signal in different ways, from top to bottom and bottom to top. And then we have sort of different distortions, and we can sort of kind of figure out why these distortions happen and how to model them out, basically. Okay. Any more questions? So we're a little bit early. I think we're supposed to sort of go till 3:30. I still have time. I'm still here. I don't know if people want to leave or they want to stick around and ask questions. I mean, they're welcome to. It's up to you guys.
I had a bit of a random question, maybe.
Okay, go ahead, Shirley.
I don't really understand what aliasing is. Could you explain?
Okay, yeah. So that's something I didn't talk about at all, I think, here. Right. So, so you refer to the parallel imaging part, I presume, right?
So to
the parallel imaging part in the tutorial.
Yeah, I think. Yeah.
Yeah. Okay. So this is a good question as well. So essentially, I sort of talked a bit about how we're trying to image our quickly to read out our signal as quickly as possible, right? This is important to minimize our distortions, to get higher resolution images. That's what we're trying to do. So one way to do this is to try to skip some of our data, right? So for example, if we have this whole K-space image, we can sort of say that, okay, we're going to skip half the columns, for example. So we're going to record exactly half our data. So basically what this means is that we don't measure this whole set of frequencies. You can try this yourself quite easily. If you sort of have sort of make a fake K-space and you just put zeros in half the columns and the other half columns you have ones, and you try to transform this, you'll see that you get this sort of earliest image reconstruction. So that means that you basically get your actual image in the middle and you'll get a sort of half image halfway through. This is just a Fourier transform property, basically. So that's what happens. And in practice, we have found out that it's still worth doing. So it's still worth aliasing our data if we can read out our data quicker. And then we can sort of try to figure out a way to unalias them to sort of get rid of it and reconstruct a high resolution image.
Okay, that makes sense. Thanks.
Yeah. Any more questions, guys? Is the course going well overall? Are you are you fMRI experts now? I don't know. I thought that you had also an fMRI session in real life, right, with an actual scanner, or am I wrong? No?
No,
okay.
we didn't.
Okay. All right. Any more questions? Last chance, and then I think I'll just probably hang up, but you can always reach out to me through email or something. I hope this more or less made sense. I don't know if it was the right level or too confusing or. All right. Well, it was a pleasure to see all of you guys. Ciao, ciao. Yeah, hopefully see you around. Bye.
Thank you.